What if I told you that beneath your feet, buried 400 miles deep inside the Earth, there's an ocean larger than all the seas on the surface combined? Not a theory, not a hypothesis, a real ocean. Discovered, confirmed. And it's rewriting everything we thought we knew about our planet. In 2014, scientists found something impossible. A massive reservoir of water locked inside a blue crystal called Ringwoodite, hidden deep in Earth's mantle. Water that's been there for billions of years. Water that might be 3 times the volume of every ocean, lake, and river on the surface. This isn't just water trapped in rock. It's a planetary system we never knew existed. An underground ocean so vast it makes the Pacific look like a puddle. And here's what keeps geologists awake at night. This hidden ocean might be the reason life exists on Earth at all. It controls our climate, regulates our oceans, powers volcanic eruptions, and without it, Earth would be as dead and dry as Mars. But there's something even more disturbing. Recent seismic data suggests this ocean isn't static. It's moving, cycling between the surface and the depths over millions of years. And that cycle might be breaking down. If you want to discover the hidden worlds beneath our feet and fall asleep to Earth's deepest secrets, smash that subscribe button. Every week we explore mysteries that will change how you see our planet. This is science that will blow your mind while you drift off. Let's journey to the ocean beneath the Earth. March 2014. A small, battered diamond arrived at the University of Alberta in Canada. It looked ordinary. A cheap, industrial-grade stone, nothing remarkable. The kind you'd find in a drill bit, not a jewelry store. But this diamond came from deep, very deep. Geophysicist Graham Pearson held it under the microscope and saw something that made his hands shake. Trapped inside the diamond was a mineral that shouldn't exist at the surface. A blue crystal called Ringwoodite. A mineral that only forms 400 to 500 miles beneath Earth's surface, in a region called the transition zone. And this Ringwoodite was wet. Not damp. Not moist, soaking wet. It contained 1.5% water by weight, bound into its crystal structure at the molecular level. That might not sound like much, but when Pearson did the math, his calculations showed something staggering. If even a small fraction of the transition zone contains Ringwoodite with this much water, there could be an ocean down there larger than all of Earth's surface oceans combined. The scientific community erupted. Some called it the discovery of the century. Others demanded proof, because what Pearson was suggesting violated everything geology had taught for decades. Here's what we thought we knew about Earth's water. It all came from space. Comets and asteroids bombarded early Earth, delivering ice that melted to form our oceans. The inside of Earth was supposed to be bone dry. Water boiled away during the planet's violent formation, when temperatures reached thousands of degrees. But Pearson's diamond told a different story. Water was already inside Earth, deep inside, locked in minerals we never thought could hold it. The diamond itself was the key to understanding this. Diamonds form under incredible pressure, 100 miles or deeper. They're carried to the surface by volcanic eruptions called kimberlite eruptions, violent explosions that rip through the mantle at supersonic speeds, bringing deep material to the surface in hours. This particular diamond formed even deeper than most, in the transition zone, between 250 and 410 miles down. And when it formed, it trapped a piece of its environment inside, that blue Ringwoodite crystal. Think of it like a time capsule, a messenger from the deep Earth, preserved in the hardest substance on the planet, telling us what conditions are like in a realm we can never visit directly. The Ringwoodite in Pearson's diamond contained water in a form called hydroxyl water, molecules chemically bound into the crystal structure. Not liquid water you could drink, but H2O nonetheless, locked atom by atom into the mineral lattice. Ringwoodite is special. It's a high-pressure form of olivine, the most common mineral in Earth's upper mantle. When olivine gets pushed down to transition zone depths, 400 to 500 miles, the pressure transforms it into ringwoodite. And ringwoodite can hold water in its structure in a way olivine can't, up to 2.5% water by weight. That's the theoretical maximum. Pearson's sample had 1.5%. That meant the transition zone wasn't just damp, it was saturated. The implications were staggering. The transition zone is a shell of rock about 150 miles thick, wrapping around the entire planet. If just 1% of that zone contains water-rich ringwoodite, you're looking at more water than exists in all surface oceans. Some calculations suggested 3 times as much. Others said 10 times. We'd been living on a water world without knowing it. The oceans we can see, the Pacific, Atlantic, Indian, Arctic, Southern, they're just the surface expression of a planetary water system that extends hundreds of miles down. But Pearson's discovery was just the beginning. It raised more questions than it answered. How did the water get down there? Was it primordial, locked inside Earth during the planet's formation? Or was it recycled, dragged down from the surface by subducting tectonic plates over billions of years? And most critically, what was it doing down there? Water isn't inert. It changes everything it touches. Water in rock weakens it, makes it melt at lower temperatures, changes how it deforms under stress. If the transition zone is full of water, it's affecting Earth's geology in ways we never imagined. Within months of Pearson's announcement, research teams worldwide started looking for more evidence. They analyzed other diamonds from deep sources. They ran laboratory experiments, squeezing olivine to transition zone pressures and temperatures, seeing if it would transform into water-rich ringwoodite. And they turned to seismology, using earthquake waves to probe the Earth's interior, looking for signs of water where we couldn't drill or sample directly. Because here's the thing. We can't visit the transition zone. The deepest hole ever drilled, the Kola Super Deep borehole in Russia, reached just 7.5 miles down. The transition zone starts at 250 miles. Everything we know about the deep Earth comes from indirect evidence. Earthquake waves that travel through the planet, bending and slowing as they pass through different materials. Volcanic rocks that bring deep samples to the surface. Computer models that simulate what conditions must be like down there. The ringwoodite diamond was a rare direct sample, a piece of the deep Earth in our hands, and it was screaming a message we'd missed for centuries. Earth's water isn't just on the surface. It's a whole planet system. By late 2014, the evidence was mounting. More diamonds with ringwoodite. Laboratory experiments confirming that transition zone minerals could hold vast amounts of water. And seismic data showing anomalies in the transition zone consistent with water-rich rock. The scientific consensus shifted. There was water down there. A lot of water. Possibly more water in Earth's interior than on its surface. We'd discovered a hidden ocean, and it was about to change everything we understood about how planets work. But to understand what this ocean is doing and why it matters, we need to journey even deeper into Earth's structure, to a realm where rock flows like honey, and the rules of surface geology no longer apply. Earth isn't solid. Not really. Beneath the thin crust we live on, averaging just 20 miles thick, lies 1/800 miles of mantle. And the mantle isn't rock as we know it. It's a slow-motion ocean of minerals, flowing and churning over millions of years. The mantle is divided into layers, each with different properties, different minerals, different behaviors. Understanding these layers is critical to understanding Earth's hidden water. The upper mantle extends from the base of the crust down to about 250 miles. Here, the dominant mineral is olivine, a green crystal made of magnesium, iron, silicon, and oxygen. Olivine is relatively dry. It can hold trace amounts of water, but not much. At 250 miles depth, pressure reaches a critical threshold. Olivine can't exist anymore. The crystal structure collapses and reforms into a denser arrangement called Wadsleyite. This marks the top of the transition zone. Wadsleyite can hold about 3% water by weight, 60 times more than olivine. Suddenly, water that couldn't fit in upper mantle minerals has somewhere to go. Deeper still, at 400 miles, Wadsleyite transforms into Ringwoodite, the mineral Pearson found in his diamond. Ringwoodite can hold even more water, up to 2.5% by weight. The transition zone, that 150-mile-thick shell between 250 and 400 miles deep, is a water reservoir, a sponge made of exotic high-pressure minerals, soaking up water that seeps down from above or rises from below. At 410 miles depth, the bottom of the transition zone, Ringwoodite transforms again. The pressure becomes so intense that the crystal structure collapses into an even denser form called bridgemanite, the most abundant mineral in Earth's entire interior. Bridgemanite can hold very little water. The transition zone is bounded top and bottom by layers that reject water. It's a trap, a zone where water accumulates, because it can't easily pass through the barriers above or below. This creates a planetary water cycle completely separate from the surface water cycle we're familiar with. On the surface, water evaporates from oceans, falls as rain, flows through rivers back to the sea. That cycle takes days to weeks. But deep in Earth, there's another cycle operating on geological timescales. Water at the surface gets dragged down by subducting tectonic plates, places where one crustal plate slides beneath another, plunging into the mantle. As the plate descends, minerals in the crust and upper mantle release water. Some of that water makes it down to the transition zone, where it's absorbed by Wadsleyite and Ringwoodite. The water-rich transition zone acts like a reservoir, storing water for millions of years. Eventually, that water is released. When mantle rock rises, pushed up by convection currents or pulled up at mid-ocean ridges, it crosses back through the transition zone boundaries. Wadsleyite and Ringwoodite transform back to olivine, which can't hold the water. The water is expelled. It rises toward the surface, sometimes all the way to the crust, where it can erupt in volcanic systems or seep into the oceans. This deep water cycle has been operating for billions of years. Water moving down through subduction zones, water stored in the transition zone, water rising back up through volcanic systems, a slow, planetary-scale circulation connecting Earth's surface to its deep interior. Dr. Steve Jacobson at Northwestern University led some of the critical research confirming this. His team didn't just analyze diamonds, they created synthetic transition zone conditions in the laboratory using diamond anvil cells, devices that can generate the crushing pressures. Found hundreds of miles down, they squeezed olivine while heating it to transition zone temperatures. And they watched it transform into Wadsleyite and Ringwoodite, just like theory predicted. Then they added water. Not much, just traces of H2O in the experiment. And the minerals soaked it up like a sponge. The water didn't pool as liquid. It didn't form pockets or veins. It dissolved into the crystal structure, molecule by molecule. Jacobson's experiments confirmed what Pearson's diamond had suggested. The transition zone can hold massive amounts of water. And his team went further. They calculated how much water Earth's transition zone could contain. If the transition zone is just 1% water on average, that's roughly 1 ocean's worth. If it's 2%, that's 2 oceans. The Ringwoodite in Pearson's diamond suggested the zone might be locally saturated, meaning in some regions, it could hold even more. The conservative estimate: the transition zone contains at least as much water as all surface oceans. The upper estimate: 3 to 5 times as much. But here's what makes it even more extraordinary. This water is ancient. It's been cycling through Earth's interior for billions of years. Some of it might be primordial, locked inside Earth when the planet formed 4.5 billion years ago. This overturned the dominant theory of Earth's water origin. We thought all surface water came from comets and asteroids after Earth formed. But if water was already inside Earth, then our oceans might be partly, or even mostly, homegrown, leaked out from the interior over geological time. There's evidence for this in the chemistry. Transition zone water has a different isotopic signature than surface water. It's enriched in deuterium, heavy hydrogen, consistent with water that's been processed through high-temperature environments deep in the mantle. This suggests our oceans are a mixture. Some water from space, some water from the deep interior, blended together over billions of years, and the mixing is still happening. Volcanoes like those in Iceland and Hawaii are erupting water-rich magmas that originated deep in the mantle, possibly from the transition zone. Every volcanic eruption is a small delivery of deep earth water to the surface. Meanwhile, subduction zones are dragging surface water back down. The Mariana Trench, where the Pacific Plate subducts beneath the Philippine Plate, might be delivering millions of tons of water to the deep mantle every year. Earth is breathing water, inhaling at subduction zones, exhaling at volcanic ridges. And the transition zone is its lungs. But this breathing isn't just moving water. It's controlling the planet's climate, shaping its continents, and determining whether Earth stays habitable. And recent discoveries suggest the system might be changing. Water isn't just sitting in the transition zone doing nothing. It's actively controlling how Earth works. Without it, our planet would be unrecognizable. Let's start with plate tectonics, the system of moving crustal plates that shapes continents, builds mountains, and triggers earthquakes. Plate tectonics is unique to Earth. Venus doesn't have it. Mars doesn't have it. Earth is the only planet in our solar system with an active, dynamic surface driven by internal heat. And water makes it possible. Here's why. Dry rock is strong. It doesn't deform easily. It doesn't flow. But wet rock, rock with even trace amounts of water in its mineral structure, is weak. It flows more easily. It melts at lower temperatures. It's lubricant for the geological machine. The transition zone water affects this in profound ways. When water-rich mantle rises toward the surface, the decreasing pressure causes minerals to release their water. This water doesn't just evaporate. It lowers the melting point of the surrounding rock. Suddenly, rock that would stay solid at 1300 degrees Celsius melts at 100 degrees. That 200-degree difference is the margin between solid mantle and molten magma. Water is the switch that turns solid rock into liquid. This happens at mid-ocean ridges, the underwater mountain ranges where tectonic plates pull apart. As plates separate, mantle rock rises to fill the gap. The decreasing pressure causes water to be released from minerals. The rock partially melts. Magma erupts onto the seafloor, creating new crust. Without transition zone water, this wouldn't happen. The mantle would stay solid. Mid-ocean ridges would freeze. Plate tectonics would grind to a halt. Dr. Wendy Pinero at Ohio State University modeled what Earth would look like without deep water. Her simulations showed a dead planet. No plate tectonics, no recycling of crust, no volcanic activity. Just a static, frozen surface like Venus, where heat builds up until the entire crust melts in catastrophic resurfacing events every few 100 million years. Earth avoided that fate because of transition zone water. The water keeps the mantle convecting. It keeps plates moving. It maintains the geological cycle that makes our planet dynamic. But water does more than enable plate tectonics. It controls climate. Carbon dioxide, the greenhouse gas that regulates Earth's temperature, is part of a cycle that depends on deep water. When volcanoes erupt, they release CO2 from the mantle into the atmosphere. Rain dissolves that CO2, creating weak carbonic acid that weathers rocks. The dissolved carbon washes into the ocean, where organisms build shells from it. When those organisms die, their shells sink to the seafloor and eventually get dragged into subduction zones. The carbon gets pulled deep into the mantle, where it stays locked up for millions of years until a volcano erupts again, completing the cycle. This carbon cycle acts as Earth's thermostat. Too much CO2, the planet warms, weathering increases, carbon gets pulled out of the atmosphere. Too little CO2, the planet cools, weathering decreases, volcanic emissions build up CO2 again, and water is critical to every step. Water in the mantle helps generate magma that brings carbon to the surface. Water in subduction zones helps drag carbon back down. Water in the transition zone stores and releases both H2O and CO2 over geological time. Dr. Rajdeep Dasgupta at Rice University discovered something remarkable. Water and carbon dioxide travel together in the deep Earth. In experiments simulating transition zone conditions, he found that water-rich minerals also trap CO2. The transition zone isn't just a water reservoir, it's a carbon reservoir too. This means the transition zone regulates how much CO2 is in the atmosphere by storing or releasing both water and carbon together. It's a planetary thermostat with a buffer. The bigger the reservoir, the more stable Earth's climate. And here's the stunning implication. Earth might be habitable because of its transition zone ocean. Venus has almost no water in its interior. Its surface temperature is 900 degrees Fahrenheit. Mars has very little water in its mantle. Its surface is frozen and dead. Earth has massive amounts of deep water, and it has oceans, continents, life. The correlation isn't coincidental. Dr. Jun Koranaga at Yale University proposed a theory. The transition zone water is why Earth's oceans have stayed stable for billions of years. On Venus, all the water evaporated into space. On Mars, water froze or escaped. But on Earth, the transition zone acts as a backup reservoir. When surface oceans threatened to evaporate early in Earth's history, water locked in the mantle provided a resupply. When ice ages threatened to freeze all surface water, volcanic activity released deep water to refill the seas. The transition zone has been buffering Earth's surface water for 4 billion years. Without it, Earth's oceans would have vanished long ago. But there's evidence this system isn't perfectly stable. Recent seismic studies show the transition zone isn't uniformly wet. Some regions are saturated with water, possibly approaching 2 or 3% by weight. Other regions are nearly dry. The water distribution follows tectonic patterns. Regions above subduction zones, where plates are diving down, show high water content. The descending plates are delivering water to the transition zone. Regions below old, stable continents show low water content. These areas haven't been fed by subduction for hundreds of millions of years. They've been drying out. This suggests the transition zone water isn't primordial and unchanging. It's dynamic, constantly being replenished and depleted by plate. Tectonics and the rate of exchange might be changing. Dr. Jacobson's team detected seismic anomalies, suggesting some subduction zones are delivering more water than before. Others are delivering less. One possibility: Earth's deep water cycle is accelerating. Faster subduction, faster water delivery, more water in the transition zone. This could eventually lead to more volcanic activity, more CO2 release, global warming. Another possibility: the cycle is slowing down. Less efficient water transport means the transition zone dries out over time. Less water means less melting, less volcanism, less CO2, global cooling. We don't know which is happening, but we know the system is changing. And changes in the transition zone water budget could alter Earth's climate on timescales of millions of years. The ocean beneath Earth isn't just a curiosity. It's the engine that's kept this planet alive for billions of years. And it's a reminder that Earth is more than the surface we see. It's a complex, interconnected system extending hundreds of miles down. But the transition zone isn't the only deep water reservoir. There's evidence of water even deeper, in the lower mantle, near the core. And what we're finding there is even more bizarre. The transition zone ends at 410 miles. Below that is the lower mantle, a vast region extending from 410 miles down to 1,800 miles, where rock meets the liquid iron outer core. The lower mantle was supposed to be dry. Ringwoodite, the dominant mineral, can barely hold any water. Scientists assumed water couldn't penetrate below the transition zone. They were wrong. In 2018, a team led by Dr. Oliver Chauner at the University of Nevada found ice. Not on the surface, not in the crust, at the boundary between the lower mantle and Earth's core. But this wasn't ordinary ice. It was Ice 7, a phase of water that only exists at pressures above 30,000 atmospheres. Ice 7 is bizarre. It's cubic, not hexagonal like normal ice. It's dense, 60% denser than regular ice, and it stays solid at temperatures above 100 degrees Celsius. Chauner's team found it trapped in diamonds from ultra-deep sources, diamonds that formed near the core-mantle boundary, almost 2,000 miles down. The diamonds contained tiny inclusions of ice. Seventh, water that had been dragged to the deepest parts of Earth's mantle and crystallized under crushing pressure. This discovery confirmed what seismologists had been seeing for years: anomalies at the core-mantle boundary consistent with water-rich rock. The core-mantle boundary is one of the strangest places on Earth. Above it, solid rock. Below it, liquid iron at 4,000 degrees Celsius. The temperature contrast is extreme, similar to the temperature difference between Earth's surface and the Sun's surface, compressed into just a few miles. At this boundary, ultra-low velocity zones exist, regions where seismic waves slow dramatically. For decades, geophysicists debated what these zones were: partially molten rock, chemically distinct layers, dense iron-rich material. Now, evidence suggests they're water-rich. When subducting slabs reach the lower mantle, they don't always stop. Some penetrate all the way to the core-mantle boundary, a journey of 1,800 miles, taking tens of millions of years. As the slab descends, pressure increases. Minerals release water. That water can't escape. The overlying rock is too dense, so it accumulates at the bottom, pooling at the core-mantle boundary. Under the extreme pressure, water doesn't exist as liquid or vapor. It forms exotic ices, Ice 7, possibly Ice X at even deeper depths, or it dissolves into iron-rich melts, creating dense, water-bearing fluids. Dr. Sang-Hyun Shim at Arizona State University simulated core-mantle boundary conditions in the laboratory. He found that water can dissolve into molten rock at those depths, creating dense, viscous fluids enriched in both H2O and iron. These fluids are denser than the surrounding mantle rock. They sink, accumulating in pockets and layers at the very bottom of the mantle. Seismic imaging confirms this. Sophisticated techniques mapping the core-mantle boundary reveal patches of dense material, tens to hundreds of kilometers across, sitting directly on top of the liquid core. Some researchers call these structures mantle plumes in reverse, pools of water-rich material sitting at the bottom of the world, heated from below by the core, slowly bleeding water and heat back up into the mantle. The amount of water at the core-mantle boundary is unknown. Some estimates suggest it could rival the transition zone, potentially another ocean's worth of water, hidden in the deepest parts of Earth. But here's what makes it fascinating. This water might be interacting with the core. Earth's core is mostly iron and nickel, with some lighter elements mixed in. Scientists have debated what those lighter elements are. Silicon? Oxygen? Sulfur? Recent models suggest hydrogen, derived from water. Here's the mechanism. When water-rich material sits on the core-mantle boundary, the intense heat causes chemical reactions. Water reacts with iron, breaking down into hydrogen and oxygen. The hydrogen dissolves into the liquid iron core. It's light enough to mix in, potentially explaining some of the core's density deficit. The observation that the core is less dense than pure iron-nickel would be. The oxygen stays in the mantle, oxidizing iron and creating iron-rich compounds that contribute to the ultra-low velocity zones. This process is called water-rock reaction, and it's happening at the most extreme conditions on Earth. It's transforming both the core and the lowermost mantle, creating chemical gradients and layering that affects how heat flows out of the core. And heat flow from the core drives everything on the surface. It powers the geodynamo that creates Earth's magnetic field. It drives mantle convection that moves tectonic plates. It determines volcanic activity. Water at the core-mantle boundary is influencing processes that we see on the surface. Magnetic field reversals, changes in plate motion, volcanic hotspots like Hawaii and Yellowstone. Dr. Thorne Lay at UC Santa Cruz has been mapping the core-mantle boundary for decades. His seismic images show structures called large low-shear velocity provinces, massive blobs of anomalous material sitting at the base of the mantle under Africa and the Pacific. These structures are continent-sized, rising 600 miles above the core-mantle boundary. They're hotter and chemically distinct from surrounding mantle, and seismic data suggests they're water-rich. Lay's hypothesis: these provinces are ancient accumulations of subducted material, billions of years of oceanic crust and water delivered to the core-mantle boundary. Piling up into megastructures, they might be the graveyards of ancient oceans, water that was on Earth's surface billions of years ago, dragged down by subduction, now sitting at the bottom of the world, and that water is slowly working its way back up. Plumes rising from the edges of these provinces create volcanic hotspots. Iceland sits atop one such plume, Hawaii above another. The lava erupting from these volcanoes carries chemical signatures consistent with core-mantle boundary sources, evidence that water from the deepest Earth is cycling back to the surface. Earth's water isn't just in one place. It's distributed throughout the planet. Oceans on the surface, reservoirs in the transition zone, pools at the core-mantle boundary, all connected by a slow, planetary cycle that's been operating since Earth formed. And we're just beginning to understand it. But understanding the deep water cycle raises an urgent question. Is the system stable? Or is it changing in ways that could alter Earth's future? Earth inhales and exhales water, not on human timescales, on geological timescales spanning millions of years. But the breathing is real, and recent evidence suggests the rhythm is changing. The inhalation happens at subduction zones: the Mariana Trench, the Peru-Chile Trench, the Java Trench. These deep ocean trenches are where Earth swallows water. As oceanic crust descends, it carries seawater trapped in its rocks. Minerals like serpentine, formed when seawater reacts with ocean crust, contain up to 13% water by weight. As the slab sinks, it drags this water down. Scientists once thought most of this water was released in the first 60 miles, squeezed out by pressure, and erupted back to the surface through volcanic arcs like Japan and the Andes. But seismic studies now show water penetrating much deeper. Some subducting slabs retain water past the transition zone all the way to the lower mantle. Dr. Doug Wiens at Washington University deployed seismometers around the Mariana Trench to track this. His team detected water signals 130 miles down, far deeper than previous estimates. They calculated that the Mariana subduction zone alone is dragging down the equivalent of 3 Olympic swimming pools of water every million years. That might not sound like much, but multiply it by all the subduction zones on Earth over hundreds of millions of years, and you're talking about significant ocean transport. Earth is swallowing its oceans. The exhalation happens at mid-ocean ridges and volcanic hotspots. When water-rich mantle rises and decompresses, the water is released. It either erupts with magma or seeps through cracks into the overlying ocean. The Mid-Atlantic Ridge, East Pacific Rise, and other spreading centers are constantly exhaling water from the mantle. Hydrothermal vents, black smokers and white smokers, are the visible expression of this process. These vents release superheated water at temperatures up to 400 degrees Celsius. Some of that water came from the ocean, circulated through hot rocks near the ridge, but some came from the mantle. Primordial water or transition zone, water released during melting. Chemical analysis can distinguish the sources. Mantle water has different isotopic ratios, more deuterium, different helium signatures. Studies of vent fluids show 10 to 20% of the water is mantle-derived. That means Earth's interior is contributing water to the oceans, even as subduction zones remove it. The question is, are these processes balanced? Dr. Sujoy Mukhopadhyay at UC Davis led a study comparing water input and output rates. His team analyzed helium isotopes in volcanic glasses, helium-3, which only comes from the deep mantle, and helium-4, which comes from radioactive decay in the crust. The ratio tells you how much deep mantle material is being tapped by volcanoes. High helium-3 means deep sources, possibly transition zone or lower mantle. Mukhopadhyay found that mid-ocean ridge volcanoes are tapping progressively deeper sources over the past 100 million years. The helium-3 ratios are increasing. This suggests more deep mantle and potentially more transition zone water is being brought to the surface. Meanwhile, seismic studies of subduction zones show slab dehydration is becoming less efficient. Slabs are retaining more water as they descend, possibly because they're colder than in the past, or because changes in mineral assemblages are locking water in more effectively. The combination is concerning. More water exhaled, less water inhaled. Over millions of years, this imbalance could drain the transition zone reservoir, and a drier transition zone has consequences. Computer models by Dr. Shun Ichiro, Karato at Yale show that reducing transition zone water by just 20% could slow mantle convection. Slower convection means less heat transport, less volcanic activity, reduced CO2 release. Earth could enter a cooling phase, not an ice age on human timescales, but a long-term cooling over tens of millions of years. Alternatively, if the transition zone is gaining water, if inhalation exceeds exhalation, Earth could become more volcanically active. More melting, more eruptions, more CO2, global warming on geological timescales. We don't know which scenario is unfolding because we can't monitor the transition zone directly. We have snapshots, seismic surveys, diamond samples, but no continuous record of how water content is changing. Some evidence suggests regional variations. The transition zone beneath the Pacific appears to be drying out, possibly because the Pacific plate is old and cold, subducting less efficiently. The transition zone beneath the Atlantic shows higher water content, possibly because the Atlantic is younger, with more active hydration of the mantle. These regional differences could drive changes in global tectonics. A drier Pacific transition zone might slow Pacific plate subduction. A wetter Atlantic transition zone might accelerate Atlantic opening. Over 100 million years, this could reorganize Earth's entire plate configuration. But there's another factor: human activity. We're altering Earth's surface water distribution. Groundwater extraction, dam construction, ice melt. These change how much water is available to be subducted. When groundwater is pumped from aquifers, less water infiltrates the oceanic crust at spreading ridges. When ice sheets melt, sea level rises, increasing pressure on subducting slabs. These are tiny effects compared to natural variability. But over millions of years, they could influence the deep water cycle. Dr. Sin-Tai Lee at Rice University modeled this. His simulations showed that even 1% changes in surface water availability could, over 10 million years, alter transition zone water content by measurable amounts. We're not just changing the climate. We're potentially influencing the planetary water cycle that operates hundreds of miles beneath our feet. Earth's breathing, its inhalation and exhalation of water between surface and deep interior, has maintained our planet's habitability for billions of years. But the breath is changing, and we don't fully understand the consequences. What we do know is this: Earth is a water world in ways we never imagined. And the story gets even stranger when we ask where all this water came from in the first place. 4.5 billion years ago, Earth was born in violence. The young sun was surrounded by a disk of gas, dust, and debris. Chunks of rock collided, stuck together, built up into larger and larger bodies. Earth assembled from countless impacts, asteroids and planetesimals smashing together, their kinetic energy converting to heat. The growing planet was molten, a ball of magma with surface temperatures reaching 2,000 degrees Celsius. At those temperatures, water can't exist as liquid. It boils instantly. Any water on early Earth's surface would have evaporated into space, lost to the solar wind. So where did our oceans come from? The traditional answer: comets and asteroids delivered water after Earth cooled. The late heavy bombardment, a period about 4 billion years ago when the inner solar system was pummeled by icy bodies from the outer solar system, deposited the water that would become our oceans. This theory had evidence. Comets are mostly ice. Certain types of asteroids, called carbonaceous chondrites, contain up to 10% water locked in their minerals. Enough impacts from these bodies could fill Earth's oceans. But there were problems with this theory. First, isotopes. Water is H2O, but not all hydrogen is the same. Most hydrogen is protium, 1 proton, no neutrons. But about 1 in 6,400 hydrogen atoms is deuterium, 1 proton, 1 neutron. It's heavier, and the ratio of deuterium to hydrogen, DH ratio, is like a fingerprint for water sources. Comets have high DH ratios, about twice Earth's ocean water. If comets delivered our oceans, Earth's water should have a higher DH ratio. It doesn't. Carbonaceous chondrite asteroids have DH ratios closer to Earth's oceans. But there's a problem. We don't have enough of them. To fill Earth's oceans, we'd need more carbonaceous chondrite. Impacts than geological evidence supports. The math didn't work. Then Graham Pearson found that Ringwoodite diamond in 2014, and everything changed. If water was already inside Earth, locked in the mantle, in the transition zone, then maybe our oceans didn't all come from space. Maybe they leaked out from the interior. Dr. Lydia Hallis at the University of Glasgow investigated this. She analyzed ancient volcanic rocks from Baffin Island in Canada. Rocks that erupted 60 million years ago, but contained magma from deep, primitive mantle sources. The water in those rocks had a DH ratio different from surface ocean water. It was enriched in deuterium, consistent with water that had been processed through high temperature, high-pressure environments deep in the mantle. This suggested a deep, primordial water reservoir separate from surface oceans. But how did water get into Earth's interior in the first place? One possibility: Earth inherited it during formation. The planetesimals that built Earth might have contained water in their minerals. Not surface ice that evaporated, but water chemically bound in crystals that could survive the heat. When these wet planetesimals collided and merged, their water was incorporated into Earth's growing mantle. As the planet differentiated, iron sinking to form the core, lighter silicates rising to form the mantle, water went with the silicates. Some water was lost. Impacts were violent enough to vaporize surface rock and blow off atmospheres. But water deep in the interior, buried under miles of rock, could survive. Dr. Jun Wu at Arizona State University tested this in computer simulations. He modeled Earth's formation, tracking where water ended up. His results showed that even with massive impacts vaporizing the surface, 30–40% of water in infalling planetesimals could be retained in the deep mantle. Over millions of years of planet building, that adds up to several ocean masses of water trapped inside Earth. This water would initially be distributed throughout the mantle. But as Earth cooled and minerals transformed under pressure, water migrated. It concentrated in the transition zone, where Ringwoodite and Wadsleyite could hold it. Meanwhile, volcanic outgassing began releasing water to the surface. Every volcanic eruption for the first billion years of Earth's Tachyphine, history brought a little bit of water, from the interior to the surface. Slowly, over hundreds of millions of years, Earth leaked an ocean out of its interior. The surface oceans we see today might be mostly this outgassed mantle water, supplemented by some water from asteroid and comet impacts. But here's the twist. Earth's water might be even older than Earth itself. Dr. Conal Alexander at the Carnegie Institution studied water in primitive meteorites, the oldest, most unchanged rocks from the solar system's birth. These meteorites contain water with pH ratios similar to Earth's oceans. Chemical modeling showed this water couldn't have formed in the hot inner solar system where Earth assembled. It was too deuterium-rich. Instead, it must have formed in the cold outer regions, beyond Jupiter's orbit, where temperatures were low enough for water ice to condense from the solar nebula. This water was then incorporated into asteroids and planetesimals, which later migrated inward and built the terrestrial planets. Earth's water is ancient. It formed in the frigid outer reaches of the early solar system 4.6 billion years ago. It was delivered to the inner solar system by migrating planetesimals, and it's been cycling through Earth's interior ever since. But there's an even more profound implication. If Earth's water came from the outer solar system, and if that water was older than the solar system itself, formed in the interstellar cloud that collapsed to create the sun, then the water in your body is older than the sun. 13. Hydrogen atoms in every water molecule on Earth were forged in the Big Bang, 13.8 billion years ago. They drifted through space for billions of years, eventually condensing in a molecular cloud. That cloud collapsed, forming the solar system. The water found its way to Earth. And now it's in your cells. You're made of ancient cosmic water that's been recycling through Earth for 4.5 billion years. From the mantle to the surface, from oceans to rain, from rivers to rocks, and back again. But understanding where water came from raises an even bigger question. Could the same process have happened on other planets? And if so, are there other worlds out there with hidden oceans beneath their surfaces, teeming with possibilities we can't yet imagine? Earth isn't the only world with a hidden ocean. We're discovering that subsurface water might be common in the solar system, and maybe the universe. Start with Mars. The red planet is a frozen desert today, but it wasn't always. Valleys carved by ancient rivers, deltas where water ponded, minerals that only form in liquid water. Mars once had surface oceans. Where did they go? Some water escaped to space, stripped away by solar wind after Mars lost its magnetic field. But recent discoveries suggest much of it went underground. In 2018, the European Space Agency's Mars Express radar detected a lake of liquid water beneath Mars's south polar ice cap. It's 12 miles across, buried under a mile of ice, kept liquid by salts and pressure. But that's just the beginning. Follow-up studies found more subsurface lakes, at least 3 additional reservoirs near the South Pole. And seismic data from NASA's InSight lander suggests water-rich rock layers deep in Mars's crust. Dr. Vashon Wright at UC San Diego analyzed InSight data. The seismic velocities indicated that Mars's mid-crust, 6 to 12 miles deep, contains fractured rock saturated with liquid water. If that layer extends globally, Mars could have an underground ocean larger than any that existed on its surface. Water that retreated underground billions of years ago when the surface froze. This has massive implications for life. Martian surface conditions are harsh. Freezing temperatures, intense radiation, no atmosphere to speak of. But deep underground, protected by miles of rock, liquid water could harbor microbial life. Mars might not be dead. It might just be dormant, with its biosphere hiding in the depths. Then there's Europa, Jupiter's ice-covered moon. Europa's surface is a cracked shell of ice. But beneath that shell, tidal forces from Jupiter's gravity generate heat. Enough heat to maintain a global ocean of liquid water. NASA's Galileo spacecraft detected this ocean through magnetic field measurements. Europa has an induced magnetic field, generated when Jupiter's powerful magnetosphere interacts with a salty, electrically conductive ocean beneath the ice. That ocean is estimated to be 40 to 100 miles deep. The ice shell above it is only 10 to 15 miles thick. Europa might have twice as much water as all of Earth's oceans combined. And it's not alone. Enceladus, Saturn's tiny moon, has geysers erupting from cracks near its south pole. NASA's Cassini spacecraft flew through these plumes, analyzing their composition. Water vapor, ice grains, organic molecules, salts, indicating interaction with a rocky seafloor. Enceladus has a subsurface ocean in direct contact with its rocky interior, the perfect environment for hydrothermal chemistry. If Earth's deep-sea vents can support life, why not Enceladus? Titan, Saturn's largest moon, might have 2 oceans, a surface ocean of liquid methane and ethane, and a subsurface ocean of liquid water beneath a thick ice shell. Ganymede and Callisto, Jupiter's other large moons, show evidence of subsurface water too. The solar system is full of hidden oceans. And that raises the question, is this common everywhere? Dr. Steve Desch at Arizona State University modeled water distribution in planetary systems. His simulations showed that planets and moons beyond the snow line, the distance from a star where water ice can condense, naturally trap water in their interiors. If that's true, then exoplanets, planets around other stars, should have hidden oceans too. Consider super-Earths, rocky planets 2 to 10 times Earth's mass. They're the most common type of exoplanet we've found. Many orbit in their star's habitable zone, where temperatures allow liquid water. We've been looking for surface oceans on these worlds, but what if the water is mostly underground? A super-Earth with 5 times Earth's mass would have intense internal pressure. Its transition zone would be deeper and thicker than Earth's, potentially capable of holding even more water. If such a planet formed with water in its interior, it might never develop surface oceans. The water could stay locked in high-pressure minerals, cycling through the interior just like Earth's transition zone water. From the outside, this planet would look dry. No reflective oceans, no water vapor in the atmosphere. But inside, it could be water-rich, with subsurface reservoirs dwarfing Earth's hidden ocean. Dr. Li Zeng at Harvard modeled these water worlds. His calculations showed that super-Earths could have mantles composed of 50% water by mass, far more than Earth's few percent. These wouldn't be planets with oceans. They'd be oceanic planets, water permeating their entire structure, from surface to core. And life? If microbial life can exist in Earth's deep biosphere, miles underground, in fractures and pores, it could exist in these water-rich super-Earths too. We've been searching for life by looking for Earth-like planets with surface oceans. But the universe might be full of worlds where life exists in hidden depths. Oceans we can't see. Biospheres we haven't imagined. The James Webb Space Telescope is now analyzing exoplanet atmospheres, looking for biosignatures, gases like oxygen or methane that indicate life. But if life is mostly underground, we might not see those gases. We need new ways to detect subsurface oceans, tidal heating signatures, induced magnetic fields, seismic activity. Techniques we've used on Mars and Europa might work on exoplanets too. The search for life might not be about finding another Earth. It might be about finding another world with Earth's hidden ocean system, ADOITT, planet where water cycles through the deep interior, where life could thrive in places we'd never think to look. And that means the universe could be teeming with life, hiding in plain sight, beneath surfaces that look barren and dead. Which brings us back to Earth, to our hidden ocean, and to a question that matters for our future. What happens if we lose it? Earth's hidden ocean isn't eternal. It's part of a dynamic system, and dynamic systems can break down. Look at Venus, our sister planet, nearly identical in size and mass to Earth. Venus probably had oceans once. Early in solar system history, when the sun was dimmer, Venus might have been habitable. Liquid water on the surface, maybe even life. But something went catastrophically wrong. Venus entered a runaway greenhouse effect. Water vapor in the atmosphere trapped heat. More heat evaporated more water. More water vapor trapped more heat. The cycle spiraled out of control until surface temperatures reached 900 degrees Fahrenheit. The oceans boiled away. Water vapor rose high into the atmosphere, where solar ultraviolet radiation split it apart. Hydrogen escaped to space. Oxygen reacted with surface rocks. Venus lost its water. All of it. And without water, Venus lost plate tectonics. No water to lubricate the mantle. No water to lower melting points and generate magma. The planet's surface froze into a single stagnant shell. Heat built up underneath. Eventually, every 300 to 700 million years, the pressure becomes too much. The entire surface melts in a global resurfacing event. Then it freezes again, and the cycle repeats. Venus is geologically dead between these catastrophic events. No water cycle, no carbon cycle, no climate regulation, just a hellish, static wasteland. Earth could suffer the same fate. If the transition zone dries out, if the deep water cycle fails, Earth would lose its geological buffering system. The consequences would unfold over millions of years, but they'd be irreversible. First, volcanic activity would decline. Less water in the mantle means less melting. Fewer volcanic eruptions mean less CO2 release. The carbon cycle would slow. With less CO2 replenishment, the atmosphere would gradually lose greenhouse gases. Chemical weathering would pull CO2 out faster than volcanoes could replace it. Global temperatures would drop. Earth would enter a long, slow cooling phase. Not an ice age lasting thousands of years, but a permanent freeze lasting millions. Glaciers would expand from the poles. The oceans would freeze deeper each century. Life would retreat to the tropics, then to isolated pockets of geothermal warmth. Eventually, Earth's surface would resemble snowball Earth episodes from 700 million years ago, when the entire planet froze over. But this time, there'd be no recovery. No volcanic CO2 pulse to melt the ice. No restart. Earth would become a frozen, geologically dead world. Life might persist in isolated deep ocean hydrothermal systems, if any remained active. But the biosphere as we know it would collapse. That's the nightmare scenario if the transition zone dries out. But there's an opposite scenario, equally terrifying. If the transition zone becomes oversaturated, if water delivery from subduction exceeds water removal through volcanism, Urtitoid. Earth could become a water world. Dr. Jun Koranaga at Yale modeled this. Excess transition zone water would eventually be released through increased volcanic activity. Massive water eruptions, like the flood basalts that created regions like the Siberian Traps and Deccan Traps, but wetter. Water would pour onto the surface faster than it could be removed by subduction. Sea levels would rise. Not meters or tens of meters like from ice melt. Hundreds of meters. Thousands of meters on continents would drown. Mountain ranges would become island chains, coastal cities, river valleys, entire nations, submerged under a global ocean, and a deeper ocean changes everything. With no exposed land, there's no silicate weathering, the process that removes CO2 from the atmosphere. CO2 would build up. Greenhouse warming would accelerate. The ocean would warm, releasing dissolved CO2 like a shaken soda bottle. Earth could transition from water world to Venus-like runaway greenhouse. The very abundance of water could trigger its own destruction. These are extreme scenarios, millions of years away. But they're not impossible. Earth's deep water cycle has tipping points, critical thresholds where small changes trigger massive, irreversible shifts, and we might be approaching one. Climate change is altering surface water distribution. Melting ice sheets are adding water to the oceans. Rising sea levels increase pressure on subducting slabs, potentially changing how much water they carry into the mantle. Groundwater extraction is depleting aquifers. Less water infiltrates the oceanic crust at mid-ocean ridges. Over millions of years, this could reduce water delivery to the mantle. These are tiny perturbations compared to natural variability. But Earth's deep water cycle is sensitive. It's maintained planetary habitability for 4 billion years through a delicate balance of inputs and outputs. We're changing the inputs. Dr. Peter Van Keeken at Carnegie Institution modeled how surface water changes affect subduction. His simulations showed that a 10% reduction in water entering subduction zones could, over 50 million years, reduce transition zone water content by 15%. That might not sound like much, but it's enough to measurably change volcanic activity and climate. We're not going to see catastrophic effects in our lifetimes, or our children's lifetimes, or even in the next million years. But we might be setting in motion changes that will determine Earth's fate tens of millions of years from now. And there's another concern. We don't fully understand the system. We've discovered Earth's hidden ocean. We know water cycles between surface and deep interior. We know this cycle is critical for climate and habitability, but we don't know the residence time, how long water stays in the transition zone before being recycled. We don't know the total water budget. How much water is in the deep mantle versus the surface? We don't know the stability. What conditions would cause the cycle to break down? We're like someone who's just discovered the engine in their car but doesn't know how it works. And we're changing the fuel mixture without knowing the consequences. Dr. Graham Pearson, the scientist who found the first water-rich ringwoodite, put it bluntly. We've discovered that Earth has a hidden ocean, and we have no idea if it's stable. For all we know, we could be living in a brief moment between cycles, an equilibrium that's already starting to shift. The planet beneath our feet is more mysterious than the space above our heads. We've sent probes to Pluto, but we can't reach Earth's transition zone. We've imaged distant galaxies, but we can't see 400 miles into our own planet. And that hidden realm, that ocean beneath Earth, might hold the key to our long-term survival. So what do we do with this knowledge? How do we protect an ocean we can't see, touch, or directly study? We can't drill to the transition zone. We can't send probes 400 miles down. But we can listen. Earthquakes are Earth's voice. Every tremor, every rupture sends waves through the planet. And those waves tell stories about the rocks they pass through, the minerals they encounter, The water they sense, seismology, is our window into the deep Earth. It's how we discovered the transition zone ocean in the first place, by noticing that seismic waves slowed in certain regions, consistent with water-rich minerals. Now, we're building better ears. The Global Seismographic Network, 250 seismic stations scattered across every continent and ocean basin, is being upgraded. New sensors can detect subtler signals. Machine learning algorithms can extract patterns from noise that human analysts would miss. Dr. Daniel Frost at UC Berkeley is using these tools to create 3D maps of transition zone water content. By analyzing how seismic waves from thousands of earthquakes travel through the mantle, his team can identify water-rich regions and track how they change over time. Early results show the transition zone is more variable than expected. Some regions are soaked, possibly holding 2 to 3% water by weight. Others are nearly dry, less than 0.1% water, and the patterns are changing. Comparing data from the 1990s to recent observations, Frost's team sees shifts. Some water-rich zones are expanding. Others are shrinking. It's like watching weather patterns, but on geological timescales. The deep Earth has its own climate. Water moving, concentrating, dispersing in response to mantle convection and plate tectonics. By monitoring this deep climate, we can predict long-term changes. If we see the transition zone systematically drying out, it's an early warning that Earth's water cycle is shifting. We'd have millions of years to understand the consequences and, hopefully, find ways to adapt. But seismology isn't the only tool. Diamonds continue to be messengers from the deep. Every year, new diamonds are mined with inclusions from the transition zone and lower mantle. Each one is a data point, a sample telling us about conditions hundreds or thousands of miles down. Dr. Stephen Shirey at the Carnegie Institution has built a global database of deep diamond inclusions. Hundreds of samples, each chemically analyzed, each revealing information about their source depth. Patterns are emerging. Diamonds from certain regions, beneath subduction zones, consistently contain water-rich minerals. Diamonds from other regions, beneath old continental cores, contain drier minerals. This geographic variation matches seismic observations. Together, diamonds and seismology paint a consistent picture. Earth's deep water is concentrated in specific regions, and those regions are shaped by plate tectonics. But we need more data. The diamond database has hundreds of samples. Sounds like a lot, but it's nothing compared to Earth's vast interior. We need thousands more. Mining companies are being recruited to help. Every deep-source diamond that comes up is a potential scientific treasure. Partnerships between industry and academia are forming. Miners save unusual diamonds for research instead of selling them to jewelers. And new technologies are enabling more detailed analysis. Atom probe tomography can analyze water content in minerals, grain by grain, revealing how water is distributed at microscopic scales. Synchrotron X-ray techniques can determine water speciation, how water is bonded in the crystal structure. Each technical advance reveals more detail about the hidden ocean. Meanwhile, laboratory experiments continue pushing boundaries. Scientists can now simulate conditions down to 1,500 miles depth, well into the lower mantle, using diamond anvil cells and laser heating. Dr. Yingwei Fei at Carnegie Institution is running experiments on water-bearing minerals at core-mantle boundary conditions. Pressures above 1 million atmospheres. Temperatures above 3,000 degrees Celsius. His results are surprising. Water behaves strangely at these extremes. It forms exotic compounds, silicate hydrates, iron hydrides, possibly even metallic water. At the very highest pressures, these experiments are redefining what water means in the deep Earth. It's not liquid, H2O. It's a chemical component that can take on dozens of different forms depending on pressure, temperature, and what other elements are present. Understanding these forms helps interpret seismic data. If we know how water-bearing minerals behave, we can recognize their signatures in seismic waves. And the more we listen, the more we learn. Recent seismic campaigns in the Pacific have detected ultra-low velocity zones at the core-mantle boundary, regions where waves slow dramatically. These might be pools of water-rich melt, sitting on top of the liquid iron core. If confirmed, they'd represent a third major water reservoir. Surface oceans, transition zone ocean, and core-mantle boundary pools. Earth's water would be even more widespread than we thought. But perhaps the most exciting development is space-based monitoring. NASA's GRACE satellites, gravity recovery, and climate experiment can detect tiny variations in Earth's gravitational field caused by mass redistribution. They've been used to track ice melt and groundwater depletion at the surface. Now, researchers are exploring whether GRACE-like satellites could detect deep Earth changes. If water moves between the transition zone and surface on timescales of millions of years, it would slightly change Earth's mass distribution. A sensitive enough satellite might detect it. Dr. Isabelle Panet at the French National Center for Space Studies is developing the concept. A constellation of satellites precisely tracking Earth's shape and gravitational field over decades could reveal whether the deep water cycle is accelerating or slowing. It's a long shot. The signals would be tiny, buried in noise from surface processes. But if it works, we'd have real-time monitoring of Earth's hidden ocean. For the first time in human history, we'd be able to watch the planetary water cycle operate. Not just the surface part we've known about for centuries, but the deep part we just discovered. And we'd have the knowledge needed to understand whether Earth's water future is stable or teetering on the edge of change. As you drift toward sleep, consider this. Beneath you, hundreds of miles down, is an ocean larger than all the seas you've ever seen. An ocean that's been there since Earth formed, cycling water between depths and surface, maintaining the planet's habitability for billions of years. You're floating on a water world, and you never knew it. If this journey to Earth's hidden ocean moved you, subscribe for more mysteries from beneath our feet. Every week we explore the planet's deepest secrets, from the core to the crust, from ancient histories to futures we can barely imagine, all designed to expand your mind while you drift into peaceful sleep. Sweet dreams, planetary explorer. And remember, Earth is stranger and more wonderful than you ever imagined.